Swayam Prabha. Digital India. Educated India.
Welcome to Structural Dynamics class. So in this class we will study about time history analysis, which is a application to multi-degree of freedom systems. So when a dynamic force is acting on the structure or in the form of say earthquake or wind, how do we analyze the structure and how do we find the response of the structure. So the outline of this class is we will discuss about how buildings are converted into a lumped mass system, which is idealized as a 2 degree, 3 degree, 4 degree freedom systems, and then how do we develop mass matrix, stiffness matrix and damping matrix for that, and then we formulate dynamic equilibrium equation, and then this dynamic equilibrium equation is usually coupled equation. So now how do we decouple these equations, the equation matrix, and then so what is a concept of participation factor, and then finally how do we find displacement when the input ground motion or input force is given to us. So first, so this is a building. So how we are converting this building into a lumped mass system. So as you can see this, we need say plan dimensions, okay, elevation dimensions. So for fixing the mass of the structure at different floors, and then stiffness of the floors. So mass of each floor, okay, usually is lumped at slab levels or say slab 1, slab 2 and slab 3. So this slab level, something like say mass from this to this location will be lumped at slab 1, and mass from this level to this level is lumped at second level, and then remaining mass is lumped at third level, and then this one will be the missing mass. So this will not be considered in this lumped mass analysis. So usually the acceleration or the inertia force generated at this place is lesser, and then these forces we consider, okay, M1, M2 and M3. So like that we have already studied how to develop stiffness matrix, mass matrix and damping matrix. So if there is any doubt, please refer to previous lectures. So this mass matrix M1, M2, M3 and the stiffness matrix K1 plus K2 minus K2 0 minus K2, K2 plus K3 minus K3 0 minus K3 and K3, and this is damping matrix similar to stiffness matrix C1 plus C2 minus C2 0 minus C2, C2 plus C3 minus C3 and then 0 minus C3 and C3. So this is mass matrix, stiffness matrix and damping matrix. So I already discussed in the previous class that all these matrices are positive definite, and because of which what roots we get are real roots. Now this is a dynamic equilibrium equation for multi-degree of freedom system. So whereas where these three terms are inertia force, damping force and stiffness force, this is externally applied force F. Now if externally applied force is say coming from earthquake, so we already derived how earthquake force or equation of equilibrium for earthquake actions. So mu double dot plus cu dot plus ku is equal to minus u double dot g into 1, because it is a matrix and force is a vector. So this vector 1 is 1 1 1. So it depends on number of degrees of freedom. So if n degree of freedom system is there, so this is n rows and 1 column vector. So we assume solution to be u is equal to phi and q. So this phi q I will explain you once again. So if I take say this as a structure, say 3 degree of freedom structure, say mass is lumped at this location, mass is lumped at second location, mass is lumped at third location. So u is the displacement of entire system. But where we are defining displacements at mass 1 point, mass second point and mass third point. So when system is vibrating because of the action of external forces, so we have to tell which location and at what time. So, which location and at what time. So, in this equation u is equal to phi q. So, phi is dependent on x, that is location, and q is dependent on time. So, q is equal to phi q. So, since it is discrete system, x takes only 3 values, like first floor value, second floor value, third floor value, or that means it is 3 meters or say 6 meters or 9 meters, assuming that each floor to floor height is 3 meters. So, 3, 3 and 3. So, this is 3 meters, this is 6 meters and this is 9 meters. So, only 3 values it takes, discrete values. Then when we substitute this u is equal to phi q in the above equation, what we get is m phi q double dot. So, why? Because q is a time variable. So, what we get from this equation is, so u dot is equal to phi times q dot. Similarly, u double dot is equal to phi times q double dot. So, like that, m phi q double dot plus c phi q dot plus k phi q. So, we are substituting u here, u dot here and u double dot in this equation, and we are getting, so this total equation is equal to minus m u double dot g. Then if we pre-multiply this with phi transpose, what will happen is phi transpose m phi into q double dot plus phi transpose c phi into q dot plus phi transpose k phi into q is equal to phi transpose m u double dot 1. So, why we are multiplying this with phi transpose? So, phi is a modal matrix, and each phi, so phi 1, phi 2 and phi 3, this is mode shape vector. So, mode shape has a property to decouple the coupled equations because of orthogonality. So, in the previous lecture, in previous classes, we have discussed these mode shapes are orthogonal to each other. So, each mode shape is perpendicular to other mode shape. If you look at graphically, you can easily assume or visualize that each mode shape is perpendicular to the other mode shapes. So, using that principle, orthogonality of the mode shapes principle, if we pre-multiply and post-multiply mode shape with a matrix, then what we get is the diagonal matrix of M, diagonal matrix of C, diagonal matrix of K. So, that will decouple the coupled equations. So, if you look at this one, mass matrix, damping matrix and stiffness matrix. So, this is a general equation of motion for multi-degree of freedom system. So, we are pre-multiplying and post-multiplying with the mode shape or modal matrix. So, if we do that, this uncoupled equations, so like this M11, M11 Q1 double dot plus C11 Q1 dot plus K11 Q1. So, this got decoupled, so uncoupled equations, minus M11 U double dot G, U double dot G. So, here M22 U double dot G. So, this is second equation. So, this is first equation, second equation, third equation. So, in a way what we have done here is n degree of freedom systems we converted into n single degree of freedom systems. If you look at each equation, it is a single degree of freedom system with changed coordinates. So, displacement function is not now anymore in terms of u. Now, displacement function has got converted into q. When we take one equation and then divide that equation by m, its own mass. So, q1 double dot plus c11 by m11 q1 dot plus k11 by m11 q1 is equal to m1 by m11 u double dot. So, this is a ground acceleration. This is the mass which is present in that first mode, and this is the mass term in the mass matrix. So, with this what we can write is, so C11 by M1 is nothing but 2 zeta 1 omega 1, K11 by M11 is omega 1 square, and this M11 by M11 is mass participation. Now, the equation of motion for the uncoupled equations, that is Q1 double dot plus 2 zeta I omega I Qi double dot, Qi dot plus omega I square Qi is equal to minus Pi u double dot G. So, this is the single degree of freedom system we converted n degree of freedom systems into n single degree of freedom systems. So out of which this I. So we can write I is equal to 1, 2, 3 up to n numbers. So what is participation factor? Participation factor is like phi transpose m1 by phi transpose m5. So if we look at this equation here, so phi transpose m1 by, if we divide this entire thing here, so the left from here, if we divide this entire thing here, it will become as phi transpose m1 by phi transpose m5. So that's what it is. This is participation factor. Now let me show you a small animation of participation factor. So like what is participation factor in multi-degree of freedom system? So if you look at this animation here, this is a total vibration of building, and this is the first mode, second mode and third mode. So what modal analysis does is n degree of freedom system is getting converted into n single degree of freedom systems. So as you can see, this is the first mode, this is second mode and this is third mode. So if I stop it here, so you can see this in time history analysis, what we want is, this is the total response. So this has two parts in it. One is phi and second quantity is q. So q is the response of that mode and phi is the response, okay, at the location. So two quantities are there. So now if we want response at this location, you can look at the arrow, okay, we need to add this plus this plus this. So first mode response at this location, second mode response at this location, top location, third mode response at top location. So if we add these three things at that time instant, we will get total response at that time instant. Similarly, second floor if we take, so this response plus this response plus this response, if we add all three, we will get this response at that time instant. Similarly, first floor level, so first mode first floor, second mode first floor, third mode first floor. So we can add all these three things to get a floor response at that time instant. So in this one, we need to understand one more important thing. As you can see here, so if I stop it, so here this is first mode, this is second mode, this is third mode. In this one, I have given here equal weightages. So 1, 1, 1 weightages I have given, but this 1, 1, 1 weightage usually will not be there in the real structures. In real structures, first mode participation will be higher, second mode participation will be slightly lower, third mode participation will be much lower. So that depends on this participation factor. So this participation factor is telling us that how much mass is participating in each mode. So that means what, how much mass is participating like for developing inertia force in that mode. So that information is given by this. Now if we look at the diagram animation here, so now what I am doing is, say first mode participation is say 60%. So first mode participation is say 60%, second mode participation is say 30% and third mode participation is say 10%. So if we look at this one, then if I start the total response, you can clearly see that the total vibration is more near to the first mode, and then less likely that these two things are also adding. You can see this slight shade of second mode and third mode. Okay, sometimes it happens that first mode itself is say dominating one. So maybe this is say only 15%, say 0.15 and 0.15, and the second mode is only third mode is only 0.5%, that is 0.05. So now if we look at it, so first mode and this are matching, almost matching, and the total response is very near to this one, even though second mode and third mode are present, but they are less likely contributing or dominating the overall response. So in some cases what happens is, first mode may not contribute much, or say its contribution is slightly lesser or equal. Say 40% is first mode, and then say again 40% is the second mode, and then 10% or 20% is a third mode. So in this one, if we look at this, now first mode and second mode both are dominating the total response. So when we look at the multi-degree of freedom system, say n degrees, say some 10-story building, 20-story building, it will have large number of mode shapes. So how many mode shapes we need to consider in doing time history analysis of say 20-degree of freedom system, say 20 floors building. So a usual suggestion is like where mass participation is more than 95%, that many modes you consider. So mass participation more than 90% means what? First mode is participating, giving say 60%, second mode is say giving say 20%, third mode is giving say 8%, fourth mode is giving say some 2%, 3%, something like that. So what we do is first mode, second mode, third mode, fourth mode we add. So we add mass participation as like if it is crossing say 95%, then we stop at that point. So we need not take all the mode shapes into consideration. So if we take first few mode shapes where total mass participation is becoming more than 95%, we can do the analysis. So that is what is the participation factor. Now, so if this is the equation of motion for that single degree of, so for that mode shape, for one mode shape. So if you using numerical methods, we can solve this one. So either you use central difference method or Newmark's method and solve this. So we can find out the solution easily for Q1, Q2, Q3. So all these are responses, time history responses for that mode shape. So using numerical technique, we can find out Qi. So I can be 1, 2, 3. As many degrees of freedom are there, that many time history responses we find out for a given component of earthquake ground motion. So as you can see this one. So this is the total response. So the response here is, so this is U1, this is U2, this is U3. So the phi 1 what we found out just now, sorry, Q1 what we found out just now is this Q. So we are giving input ground motion somewhere here, T and acceleration. So with this one we decoupled equations in 3 mode shapes or 3 mode shapes. N degree of freedom system is converted into n single degree of freedom system with this mode shape. So mode shape 1, mode shape 2, mode shape 3, as you can see here. So when we do that, so we got time history response of first mode, time history response of second mode, time history response of third mode. So in this participation factor is included in it. So now we want to find out U1, U2, U3. So how do we get U1, U2, U3? So this Q1 multiply by pi 3 of first mode plus addition of Q2 multiply by phi 3 of second mode plus Q3 multiplied by phi 3 of third mode. If we add all 3, we get U3. So that is the final solution. So it is something like that. Okay. So Qi phi ij. Now what we get is this. So for first mode, you can see this one. Okay. So Q1, Q1, Q1 all. So we get Q1 of 3, Q3 of 1, Q2 of 1, Q1 of 1, and then we get this. So story 1 U1, story 2 U2, story 3 U3. So Q1 of first mode, Q1 of second mode, Q1 of third mode. If we add all 3, this we get U1. Q2 of first mode, Q2 of second mode, Q2 of third mode, we get displacement of second story. Q3 of first mode, Q3 of second mode, Q3 of third mode, we get displacement at third floor. So first mode, second mode, third mode response, addition of that is equal to total response. So in summary, what we have studied in this class. So in this class, we have studied how to decouple the coupled equations. So what we have used is phi matrix or phi vector, which has an important property of orthogonality. So if you pre-multiply and post-multiply phi matrix with a mass matrix or stiffness matrix or damping matrix, it will decouple the equations. So that means what? It will remove the off diagonal terms. So leaving us with the single equation. So 3 degree of freedom system gets converted into 3 single degree of freedom system. So what we call this as modal analysis. So modal analysis means converting n degree of freedom system into n single degree of freedom system. So, and then we have, after converting that, we have studied how to find out the time history response if ground acceleration is given. So, and then finally we have added this by using modal participation factor. So, this modal participation factor comes from phi transpose m1 divided by phi transpose m5. So, this modal participation factor will tell how much mass is participating in first mode vibration, how much mass is participating in second mode vibration, how much mass is participating in third mode vibration.